So, nice to meet you, everybody. My name is Idan Bassuk, and I'm the head of AI at Aidoc, where we use technologies of object detection and image segmentation to detect urgent medical abnormalities in different medical imaging modalities, such as CT scans. And it's nice to see some familiar faces here in the crowd. Thank you all for coming. And today, I want to share with you and talk together with you about some of the three most interesting papers in object detection of the last year or so, which have done really amazing things that are really relevant to the challenges of medical imaging data. So, first of all, a little bit about object detection. So object detection is progressing really quickly. Just between 2016 to 2017, in the leading benchmark, the COCO competition, the accuracy has raised in about 20% relatively between the years. So the bottom row is the best submission of 2016, and all of these four are the submissions from 2017 challenge that was in the end of 2017. And not only is it a mature and quickly advancing technology, I think it's also a very transformational technology. And it has the potential, and I really believe that it will transform any and every industry, be it medical imaging, defense and business intelligence, robotics and autonomous vehicles, and even augmented reality, and many, many other more industries. Okay, tada. And the reason I really like these meetups and talks is because I think that object detection and deep learning in general is a very, very, it has a lot of potential, but we wouldn't be able to fulfill this potential fast enough if you won't have a lot of people that really understand this field. And the problem with that is that we are building a mountain of papers that are really hard to read, are really hard to get into. It takes hours to really understand them, especially if you want to dive into the little details that are relevant to really implement something, especially if it's on new data. And I was really inspired by this article on Distill, which was called Research That, and talked exactly about that, and I really recommend you to read it. It was written by Chris Ola and Shen Carter, two research scientists from Google. And what they say, and I really agree with them, is that we really need to look at this mountain, and instead of we can continue making the mountain bigger as long as we build staircases and elevators that enable everyone to climb it together with us. Because if we won't have enough engineers that understand the state of the art, we wouldn't be able to create an applicative solution fast enough. And I've personally invested hundreds of hours in learning this field, and I still have a lot more to learn. So, after investing a lot of time in it, my conclusion is deep learning is advanced, and it's mind-blowing, and it's creative, and you need to dive into it and learn it seriously in order to understand it, but it's not rocket science. And by the way, I think that even rocket science is not really rocket science. And my question is, what can we do to reduce the time that is required for the next people to join this field by a factor of 10 from the time it took me to join this field? And I think that if we it should be a community effort, and we should spend more time on trying to make these things more explainable, more easy to understand, use the right explanations and the right visualizations, and that's it. So now let's dive into first the structure of this talk. It's going to be about an hour and a half. First, I will talk about the challenges in medical imaging data, and after that, I will dive into, it depends on how much time we will have, 2 to 3 of the most advanced papers, deformable convolutional networks, feature pyramid networks, and focal loss. I guess most of you heard these names if you're in the field. And I'm going to, these 3 papers address most of the challenges that I'm going to present now. And they do it in a really nice way. And I'm going to explain them in a way that is relevant both to the medical imaging domain and explain the unique details that are relevant to apply it in the medical imaging domain, but also it will be relevant for any one of you that wants to understand these concepts and take them to other fields as well. So let's start with the challenges of medical imaging data. By the way, can everyone hear me well? I don't think I asked. Okay, if someone can't hear me, just say. The bottom of the screen? Well, I'm not sure I can solve that, but you're welcome to come closer. So the first challenge is extreme class imbalance. Objects are very small and rare compared to the number of images and the image sizes. What I mean with that, you can see here this arrow is a detection of one of our algorithms in a brain CT scan of relatively medium-sized, very urgent finding in the brain. And this is relatively large compared to many of the findings that we are required to detect, and it's relatively obvious. I put it here because I think that even that is not considered large in terms of classic object detection. And I wanted you to understand what I'm talking about and really see it. So, and we're talking about findings that are sometimes smaller than 10 by 10 pixels, and they are found in images which are a single image is actually a 3D image for us. It's not a 2D image. So it can be 10 by 10 pixels over a few slices inside an image which is 100 slices, 100 2D images, or even more. So the finding is a very small part of the brain, and most of the scans are of healthy brains or healthy spines or whatever. So the interesting data, the data that we want to detect, is very rare. And that's a very big challenge. The second challenge is that the objects and our background, which is the anatomical structures, in my opinion, are relatively much less well-structured, much more deformable, and less rigid. If you can, we can take an example, which of course we can find hard example in the classical dataset as well. But if you look at a wheel, it is bounded pretty well by a square bounding box, which is the classic use case of object detection. But here is a part of a brain, and you can see that these pixels that I highlighted in yellow, it's not their original color. This is a single finding in the brain. So if I put the tightest bounding box that I can around this finding, it will still contain a lot of uninteresting pixels. And then when I will extract the features for this bounding box, most of the signal will come from background rather than from interesting pixels. And that's part of the shapes of the object being less deformable. Another challenge is that the images are 3D and they're large, and there is a lot of difference between images of cats to CAT scans. And actually, you can see that the difference in sizes, the inputs are could be 30 times larger, and the objects are nominally 10 times smaller. And this is a challenge in terms of computation power that is required, the time that it takes it to converge, and the memory footprint of your networks, and how you can find a good compromise in the design of your model and what input to use. And the last challenge that I will talk about is that when a radiologist analyzes a CT scan, he doesn't just look at the current CT scan. He looks at a lot more types of data. The demographics of the patient, his age, the referral letter of the doctor that referred him to this scan, his past scans, and the reports that were written on these scans. And actually, the radiologists are, not only they do this, but they are obligated to do this by regulation, and for a reason, because not all the information is in the image. And if you don't look at the past, you can't really diagnose some of the cases. So how do you combine all the different types of data, both visual, text, and structured data?
You include the other metadata? You include the other metadata as well in the
Okay, so now I want to dive into, as I said, 2 to 3 papers. And the first paper I wanted to start with is Deformable Convolutional Networks. And that's the paper I chose because, from my experience, a lot of people are kind of afraid from this paper and find it very hard to get into. And I think that it's not that difficult if you understand it, if you explain it correctly. So what is the motivation for the by the way, this paper is by the Microsoft Research Asia group. And it's been for the last 2 years, both in 2016 and 2017, a significant component of one of the top 3 entries to the COCO object detection competition. So it's a very significant boost to performance. And it's by Microsoft Research Asia, which is one of the top object detection groups, in my opinion, in the world, and gave some of the top contributions in the last years. So the motivation for this paper is that neural networks and the popular mechanism that we use with neural networks, with convolutional neural networks, such as data augmentation, know how to deal pretty well with simple transformations, such as translation and rotation. But non-rigid transformation, like changing the pose or the viewpoint or just the object being of a less clear and regular form, are much more challenging for neural networks to deal with. And how can we answer that challenge? So the solution is to give the network a capability, a dynamic way to control the receptive field of the convolution. So instead of using the traditional convolution that samples the image with a square grid, we can why not sample the image in any shape that we want? And why not have it adapt to the input, the shape that we sample the image with, adapt to the inputs that we get, to our images and objects. So we didn't talk yet about why should it solve the problem that we are talking about, but we will see it in a minute. But we don't only want to implement this solution if it works. In order to be applicable in the industry, we want to do it to implement something that is easy to train, and preferably end-to-end. We don't want to train several different components and then combine them. It creates a very cumbersome research process. We don't want to increase the model complexity, its runtime and training time and number of parameters too much. And we don't want to increase the code complexity. If it's a convolution, when I define the model architecture, I want to write deformable conv2d and put the parameters inside it, just like I write conv2d today. And I want it to be proven on challenging tasks rather than just toy data sets. And earlier works in similar, that try to deal with similar problems to this, such as spatial transformer networks, gave major scientific contributions, but in the paper they only proved it on toy data sets, and many people that tried to apply it on real-world data sets found it very hard to make them converge at all. So these are our requirements from this solution. And now let's talk about the components of this solution. And there are actually 2 components, and they build them on top. They can be combined with any object detection architecture and the meta-architecture, like faster RCNN and RFCN. These are the 2 architectures that they demonstrate in the paper. And the first component is the deformable convolution. And the concept is we keep convolution the same, except for making the sampling location a function of the image. The sampling location are not a fixed grid, they are a function of the image. So a few examples that they give in the paper is that the receptive field after several convolutions of a neuron in this area of the image will be each of these in the area of each of these red points in the image. So the value that we get from that is that you can see that the pixel this neuron is is on the sky or on the border between the sky and the mountains. And if we had used traditional convolutions, after 3 convolutions, we would get like a square, or effectively it would be like a circular or Gaussian shape around that point. But now with deformable convolutions, we are able to sample a very large part of the sky, the mountains, and the objects in the image. And intuitively, it looks like a desired property, because if I'm just seeing blue pixels, how can I know if it's sky or water or like a wall in that color? I can't really know that for sure unless I have larger context. And when they use the same network, but they look on a different part of the image where there is a far motorcycle, the same deformable convolution mechanism creates a much more dense, spatially dense receptive field, which covers a much smaller area and samples the objects very tightly, and also samples a bit of the object background, because it's intuitive that we want to sample not only the object, but the background as well. And on a closer and larger object, we can see that the receptive field is larger and a bit less dense, but does cover, again, the entire object instead of just a rectangular or circular part of it, and the background as well. So this is the value that we can get. This is an intuition for the value that we can get from these deformable convolutions. And this was the first component, which we will dive into the implementation of this component in a few slides. But first, I want to talk about the second component, which is deformable ROI pooling. So first, let's do a short reminder of faster RCNN. And in faster RCNN, we get an input image. We put it through a feature extractor, and we get a feature map. Okay, I'm assuming that you know faster RCNN or similar models, and I'm just giving you a really short reminder. Then using this feature map, we predict about, let's say, 2,000 bounding box proposals. And about 2,000 bounding box proposals. And some of them, a few of them, really cover the objects that we are interested in, such as the cars. But some of them are just false positive of our bounding box proposal mechanism, and they lie on the background. And then we take each of these bounding boxes and we crop them from the feature map. One by one, we crop them from the feature map, and we have like 2,000 crop feature maps for the different bounding boxes. And then we put each of them through a second feature extractor, which is also called, the first part is called RPN, Region Proposal Network. The second part is called the second stage, or fast RCNN. And at the end of this feature extractor, we classify each bounding box and refine its coordinates with a regression head. So the deformable ROI pooling changes the implementation of how we crop each of these proposals from the feature map. So what is actually deformable ROI pooling? Instead of cropping a rectangular bounding box, a single rectangular bounding box, we pool 9 separate bounding boxes. And we'll see how it actually works in a few minutes. We pull 9 separate bounding boxes, and that way you can see that these objects, and that's an example from the paper, are able to cover the object of interest much more tightly. And the features that are cropped from the feature map are much more relevant to classify the object of interest and are not wasted on background, which in large amounts in deformable object is less interesting and valuable for us. So this was the description of the different components, and it shows a very strong improvement in both of the significant metrics in the world of object detection. We have 2 metrics, the COCO metric and the Pascal-Vogt metric. This is the COCO metric, which gives more weight to accurate localization. How well am I giving tight bounding boxes around the object? So this tight localization metric gets about 5 to 10% relative improvement due to this solution. And the second metric, which gives less weight to tight localization, and thus it means its value is actually by telling us, giving us more insight into how many objects we are missing or detecting, how many objects am I not detecting at all, etc. So this metric, by the way, is much more important, in my opinion, to medical imaging applications in most cases, because tight localization in many times is less important, but if we miss a medical finding, a critical medical finding, that's something that the doctors will really be mad at us about. So this metric is also improved by 5%.
From the paper, hours? Hours from the paper?
Sorry?
Hours from the paper?
The what? Sorry?
Hours.
Yeah, that's the hours here in this table is their implementation of, for example, faster RCNN with deformable convolutional networks.
What does it mean? 50% of the objects?
5%. 5%, not 50. Oh, 51. It's the Pascal-Vogt mean average precision metric. I don't want to dive into that too much. Just take it as a score for how good your detector is. It's not really important to understand it right now. Okay?
But what is the percentage of the undetected object?
What is the percentage of undetected object? It is not, you can't understand it from this number, but you can only understand that it has increased by a significant amount. It is improved by a relatively significant amount. You don't know the exact number of undetected objects because this metric covers a lot of different working points of sensitivity, of recall and precision that you can choose for your algorithm. Okay, so now let's talk about the implementation. By the way, after that, you can ask questions freely. So please keep your questions to the end of this part if you have any more questions, unless they are really important. So first of all, let's start with the implementation of deformable convolutions. So this is the diagram that they have in the paper. And I think that it's confusing a little bit because it's a good diagram, but it contains too many levels of abstraction. And it's hard to wrap your minds around what's going on here. So I invested some time in decomposing this diagram into several parts, so it would be easier to understand. So this is the essence of the layer, which is called deformable convolution. The essence is that we have an input feature map. It doesn't have to be the image. It's actually, most of the time, it's not used directly on the image, but on deeper layers, on deeper feature maps. And we use a convolution all over this image, but the convolution is not the old square 3x3 convolution. It's a different sampling grid for each location of the convolution. And then let's say that I'm talking about this location. So I have 9 points that I'm sampling in the locations of the blue squares. And then those nine points are transformed into 1 point, just like in the regular convolution, the 3x3 square was converted into 1 point or one vector in the feature map, one spatial location. So this is the essence. Now the implementation. So you start by doing a regular square 3x3 convolution. Ignore the blue squares for now. You start with a regular 3x3 convolution with a square shape, and the output of this convolution is a feature map, which size is relatively the input feature map spatial size, but the depth of this feature map is about 9 times 2, 18. Why 9 times 2? It's because we can visualize it. This is just an aid to understand it. This is not a stage. This is the last computation that happens here, actually. But each 18 vector of length 18 can be seen as 2 squares of size 3x3. So the top left elements in these 2 squares give us the offsets that tell us where to locate the top left sampling point of our sampling grid. And the center squares in these 2 squares tell us where to place the offset that tell us where to place the center blue square in our new sampling grid. And because we have 9 squares, 9 elements in each of them, we get the offset for each of our new blue squares. And yeah, that's it. So now that, so 1 square, of course, is the horizontal offsets. Tell us on the left to right axis how much do we want to move each of our squares. And the second square gives us the vertical offset. So then we take this offset and we just sample them from the input feature map, sample them, multiply them with the weights of our convolutional kernel, and get the vector. And there's a little bit of a problem with what I just described, because this convolutional layer is a convolution, so it outputs continuous valued real numbers. It doesn't output integers. But we need to sample, in order to sample the image, the image is discrete. It contains discrete pixels, so we need the integers. But the problem is that we can't round these numbers, because then it wouldn't be differentiable. So, and then we wouldn't be able to backpropagate through it, or it will require a much heavier solution and a much cumbersome solution. So what we do, it's something that this group mentions a lot in their papers. Imagine that we have just like, if we wanted to just, if we had 2 coordinates, the x coordinate was 2.3 and the y coordinate was 7.2, and we wanted to sample it from the image. So, and we wanted to sample them from the image, sample this point from the image, we could use bilinear interpolation in order to like, to interpolate what should be the value at that point. So fortunately, bilinear interpolation can be implemented very efficiently using matrix operators and matrix multiplication. And that's why we can do it for many points of the sampling grid in real time, and even on the GPU, of course. So explaining, it's not very complex to understand how this, the implementation of the matrix-based bilinear interpolation work, but it is outside of the scope of this talk, and if you're interested in it, you can come talk to me about it later. Okay, so that's about the first component. By the way, if anyone has a question about this component, ask, because maybe it's a better time. Yeah. 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 Right, so.
But then you said that the blue things you apply your camera with, the same yellow thing that you apply on the
No, those are, okay, so I'll repeat the question so everyone will hear. So I said that, first of all, before I do the convolution with the square, the yellow square, the regular convolution, I don't know the offsets for where I want to locate my blue sampling grid of the deformable convolutions. And then I said that when I know these sampling points, I take them and multiply them with the convolution kernel. And what's your name? Lisa. And Lisa asked me if it's the same kernel, if the same kernel is used for both of these convolutions, or it's a different kernel. So it's a different kernel between the yellow convolution has a single kernel, and the blue convolution has a different kernel. Okay? And they are learned separately. Okay? Any other questions? Yeah.
Does it make some discontinuity in the result? Because we jump
What do you mean?
something.
Mm-hmm.
When you sample image, you have the nitrous. Here you jump, maybe you can use from that.
Probably, but empirically it improves the result. So I guess it has some drawbacks, and maybe this solution can be improved, but it has also desirable. He asked me if it maybe it creates some discontinuity because of the weird sampling strategy. So probably it has some disadvantages, but even the convolution that we are using today also has disadvantages. So I think the only question is which mechanism has more disadvantages relative to its advantages. Yes?
So how do you propagate the gradients for the offsets?
Yeah, so when you get the loss, you backpropagate them, just like through your bilinear interpolation operator that I talked about. So you get from you have these numbers and you multiply them with a matrix of a bilinear interpolation, and then you get these values. Okay, it's not that you do something active to sample them. It's just like you have a a matrix which is a bilinear interpolation kernel, and you multiply it with these numbers after some vector operations, and then you get the values that are sampled in each of these points, and then you multiply them with another matrix. So it's backpropagated through the bilinear interpolation operator. Yes?
Is there a different sampling patterns for each pixel in the image?
Oh, I hope I understood your question. He asked if there is a different sampling pattern for each pixel in the image. So I'll go back. I hope I understood your question. I'll go back to the example images that I showed here, and I hope this answers your question. You can see that for this pixel, the sampling is much more has a much wider coverage, and for this pixel or activation, the coverage is much smaller, and the receptive field is a function of the local input. And just a second. For each location in the image, the offsets are a function of these 3x3 pixels in the input feature map. So, of course, that you will get different offsets if you place your convolution here or if you place your convolution here. Does that answer your question?
Does this mean you have depends on the input? So it depends on the original convolution?
It depends on the yellow convolution. Yes.
The yellow convolution determines
the offsets, yes. The yellow regular 3x3 2D convolution, square 2D convolution, determines the offsets. And of course, that the output of the convolution is different for each part of the image because its input is different. Okay? And that's why the offsets will be, that's the mechanism that enables, just a second, that enables the offsets to be different between different parts of the image. Okay?
So the output of the original convolution goes into the, doesn't come out to the output image, it goes to the 9x2 or something?
The output of the original square convolution enables us to sample the image for the real convolution, for the deformable convolution, which is, and that convolution is the one that really creates the next feature map of our feature extractor.
So somewhere in the green,
Hmm?
green matrix, answer
Combination of square regular convolution
Mm-hmm.
across the image will actually coordinate where it's going to line convolutions.
I'm sorry, I'm not sure I understood. Okay. Okay.
There's some memory of it because only the starts.
Wait. There are some. Please. I would like to answer your question, and I prefer to. I think it's better that we cover less papers, but I understand them better. But please keep it to only like if you have gaps to understand what I just explained, and don't be shy to ask because I'm sure that you are not the only one that didn't understand. Yes.
Does it think every pixel in the original feature map now has 18 parameters for its own convolutional, for its own deformed convolution?
Can you speak louder? I didn't hear you well.
That every pixel in the original input, for each pixel you store 18 parameters for its own special unique.
Sampling grid, yes. For each pixel in the original, for each spatial location in the original feature map, we have different 18 values that determine the real the new sampling grid, the deformable sampling grid, and this sampling grid is different between between spatial locations. Okay? Yes. I will love if you could keep this question to after we finish covering this paper, and I also have an example of the reason I think it's interesting. Okay? Thanks. Yes.
So it's only one layer?
The layer that generates the offset, only one layer, and it's even a linear layer. It doesn't have a non-linearity.
Would you consider only one layer and not more? Because if you take the same, let's say there is a pattern in the original image, and you use the same convolution, and the same pattern repeats in different places, then the deformation would be the same, right?
Yeah, I think it could be an interesting paper to try it with more convolutions and see if it...
I get the point, like if there is a different pattern, it will be the same information, and it's kind of weird, right? Because
Sorry? What do you mean?
If we have a numerous number of tumor might be right, we assume in medical imaging that probably there's only a single tumor. So you're not gaining much. But if using the same technique, when you use background or stuff like that, it might be used better.
I'm not... can you ask again, Uri?
if you take the same pattern, let's say horizontal lines, right? Within a tumor, and horizontal lines out of the tumor, and the convolutional window receptive field solve the same, it will generate the same deformation receptive field, right?
If I understand your question correctly, if the yellow convolution will be on different locations in the image, but the values of these locations will be equal, then the offsets will also be equal. Is that your question? Okay. So, yes. Okay. Can we move on? Yeah.
So the offsets are limited only to the grid of rectangular 3x3.
No, the offsets are not bounded.
The offsets are bounded because this is the information, all information that they gather from in order to reach the offset that they compute.
But so mathematically, nothing bounds these offsets, and we also know that from traditional, he asked if the offsets are bounded to the area of this 3x3 square, and the offsets are not bounded, and usually they are larger than this 3x3 square, because even in traditional object detection, we know that we can use a small convolution kernel to predict much larger bounding boxes that are larger than the receptive field of this kernel. So it's like if you look at my torso, you have enough information to know that my head is up to here and my feet are down there, right? So you can infer the wanted sampling points, even if you are looking just on a part of an object.
So it has a certain memory or something that is learning through time, so it can predict a much larger scale than the sampling region.
No, it just uses the features that it has, and just limited spatial context is enough to predict something, to infer for something that is outside of your context. Okay? Okay, yeah.
Can it be that after we impose the convolution, the set of all the pixels don't cover all the original pixels? Should we ensure that it will happen, or are we actually looking at something that should be excluded from the convolution?
Okay, good question. She asked if after we, guys, can you be quiet so people will be able to hear? Thanks. So she asked if after we do these deformable convolutions, maybe there are pixels that are not covered by our blue pixels all over the image. And yeah, it can happen. Nothing ensures us that it doesn't happen, and it's okay that it happens. Because maybe these pixels are...
No information there.
Yeah, maybe the information there is less relevant. Yeah. Or maybe it's possible that we also miss something that is important, but if it happens that if it's important, it means it will harm our classification results, and then in the backpropagation, these weights that generate the offsets will adapt to predict better offsets. So, yeah.
Are there any restrictions so that all the offsets will coincide at the same point?
What do you mean?
Like if you have very strong signal somewhere and you don't have any relations between the small receptor with the offsets, so is it possible that all the offsets will point to the same location?
I'm pretty sure that like in the formula, there is nothing that prevents it, but I guess, I guess it's something that just happens because I guess it's not really beneficial in any way that they will converge to the same sample the same point, and then the ways that are learned are like naturally sample different points. Okay, so let's move on. I just want to see how much time we have. Okay, we're good. So now let's move on to the second component, which is the deformable ROI pooling. And I just want to give a quick reminder of the regular ROI pooling, and there are many ways to perform ROI pooling. They are also called ROI warping and other names. So now it doesn't really matter. It can work with all of these methods. And I'm going to demonstrate it with the original ROI pooling, which, by the way, is not differentiable. And OK, so by the way, it's not differentiable. And the solution that I spoke about here is also the solution to make ROI pooling differentiable, or one of the solutions to make ROI pooling differentiable, the solution with the bilinear interpolation operation. So how does ROI pooling work? So from the RPN, from the first stage of the faster RCNN, we get a bounding box proposal. And then we split this proposal into several bins. For example, 2 by 2 bins, or in reality, it's 7 by 7 or 14 by 14 in most of the cases. But for the simplicity of the example, let's assume it's 2 by 2. Then for each of these bins separately, we perform max pooling on the entire bin. It doesn't matter the bin size. We perform max pooling on the entire bin. So for example, for this bin, we get 0.74. For this bin, we get 0.39, etc. So it can be max pooling. In the paper, they talk about average pooling. It doesn't really matter. And this is the original ROI pooling. And deformable ROI pooling, the idea is that we keep the same bins, and we have the same sizes for these bins, but we take each bin, keep its size, but give it an offset. So we take the top right bin, and we place it somewhere here. And take the top left bin, and we place it somewhere here, etc. So in reality, we have like 7 by 7 bins, and we predict offsets for all of them. And that's basically how it works. So the implementation is very similar to the previous implementation. It will be very easy to understand now. So this is the input feature map from which we crop, we perform the ROI pooling on. This is the feature map that we pull the ROI from. So let's say we have an ROI. This is and in this example, all of their diagrams are for 3 by 3 bins. I just mentioned 2 by 2. They do it with 3 by 3 bins. So we have an ROI when we split it to 3 by 3 bins. Again, it's the 3 by 3 yellow square here. And then we do the regular ROI pooling on this ROI, and we get the downsampled ROI. And then we put this ROI into a fully connected layer. And again, we get a vector. This time we get a single vector for this ROI of size 18, and we can look at this vector as 2 squares of size 3 by 3, which are the horizontal and the vertical offsets for each bin. So the value in the top left part of these squares is the offset for the top left bin. And the value for the top right, the 2 values in the top right part of the square is the offset for the top right bin. And that way, we can get an offset for each bin and place them in sample different parts of the feature map with them. And again, we need to sample the bins and do max pooling on areas that are coordinates that are not discrete. And this is also solved using the same bilinear interpolation matrix multiplication that I mentioned earlier. So some really cool examples from their paper on how how deformable RI pooling works. So you can see that this is the original proposal. The yellow is the original proposal. And then the 9 different bins are, we pull the original proposal and we put it into a fully connected layer and actually predict offsets which give us 9 different bounding boxes, which are the bounding boxes in red. So you can see how nicely they cover the cat, and the less relevant information here is not, we don't waste any capacity on it. So I think this is really elegant. And another example, which we have a good bounding, this is an example of the pose problem. So the woman is reaching her hand forward, and thus the bounding box that covers her has a lot of wasted space that we will waste our pooled features on the features of this background, and it speaks for itself, I think. And regarding how this can be useful for medical applications, I think that, yeah.
So can you explain a bit about how you can make for making parameters, 18 offsets, 9 bounding boxes?
Yeah, sure. It's good, great that you asked, because this is the basics. So this is the most important thing that everyone will understand. So I will explain again how from the 18 offsets, how from the 18 numbers that are the output of the fully connected, you can get 9 different bounding boxes. Okay? So, by the way, should I explain it again also for the deformable convolutions or just for the deformable ROI pooling? Okay. So when you get 18 numbers, the yellow 3x3 structure here is the original, each sub-square, each of these 9 sub-squares are the original bins, the original 3x3 bins of the original proposal. And we know the location of the coordinates of the center for each bin. It can be calculated easily. So now I have their center, and I have 2 additional numbers. I have for this top left square, I have its horizontal offset. For example, if the offset is minus 2.5, then I know that the new center for the top left bin will be placed in a minus 2.5 offset in the horizontal axis compared to the original center of that bin. And I take the value from this square, which represents the vertical offset, and if the value is minus 3.1, then I know that the center will be located minus 2 in the vertical axis and minus 3 in the minus 2 in the horizontal axis, minus 3 in the vertical axis, and I repeat this process. It's performed in a vector operation, but this process you can imagine that it is repeated 9 times for each of these bins. And that way we can get the new sampling points of our grid. Do you think it was more understandable right now? Okay, great. So if we look at the medical case, so I will come back to the same example that I showed earlier, and I think this demonstrates pretty well how one finding that can be detected pretty nicely, but when you want to classify it, if I just took this ROI and I pulled it and I put it through the second stage of my detector, then most of the information, most of the features that will be pulled will be healthy pixels, healthy brain pixels. So it increases the chances that the classifier of the second stage will misclassify this example as a healthy example. So if I use the deformable ROI pooling, I can, it naturally covers the objects, the interesting object in a much tighter way, and then the pooled ROIs are, the pooled ROI is the features in the pooled ROI are much more relevant to the non-healthy pixels in the image. Do you think this answers your question from before? Okay, great. Yeah.
The final region, the ground truth is still one region. It's not the pooled region, right?
The final region, you mean the final prediction of the model?
Yeah.
The final prediction of the model will still be this yellow square, this yellow rectangle, the original proposal of the yellow rectangle, or a single rectangle. It will not be the original proposal. It will probably be refined by the second stage, but it will be something like this original proposal. But these nine different bounding boxes help us classify and refine the coordinates of this bounding box much better.
So you have at the end a normal region proposal layer. You have to have it to have a proposal.
Sorry?
You said you replace it with these deformed regions, so you propose different regions.
Mm-hmm.
But at the end you have to have a normal region proposal layer, otherwise you won't have one box.
Yes. Not at the end. At the first stage, at the beginning, you have a normal region proposal layer. You get the proposal, and then you take this proposal, you do regular ROI pooling on this proposal, you put the pooled original proposal into a fully connected layer, and then you get the offsets that enable you to locate these red rectangles on the image. These rectangles are passed, the features under these rectangles are passed to the second stage of the detector. The second stage uses these features to classify the original yellow rectangle. And the final output, it doesn't matter where these red rectangles will be placed, the final output of the entire detector will still be something like a single yellow rectangle around this proposal. Okay? Okay, great. Some best practices. So first of all, they tried it on the last layers only. The meaning of that is that they only try to model, to use this to model deformation in high-level features. You can think of it, it's very intuitive when you look at something like this change of pose, and you have a feature for a hand, and a feature for a head, and a feature for a torso, and that way you can model their locations in an irregular way. And they try to use it on more than the 3 last layers, and they gave them diminishing returns. So they use ResNet 101 layers in this paper, and this is the end of ResNet 101. These are the last 26 layers. So this is the last ResNet block, and this is the one before it. So a large amount of the convolutions in ResNet are 1-by-1 convolutions, and of course it's probably less interesting to do something deformable with the location of these convolutions. So you have 3 blocks like this. So the optimal configuration was to put the deformable solution on each of these 3-by-3 convolution. And when they tried it on some of the convolutions out of these 23, it didn't give them too much value. In addition, what's really amazing about this solution is that it answered our requirement of not adding a lot of complexity to our model. And the number of parameters in the network barely increased. And also the inference time for a single image didn't increase significantly, which is very nice. And
the image per slides.
Per
Slides of MRI.
Right. So yeah, their work is on 2D images. So of course, yeah, adapting it to 3D is more advanced. Just like 3D convolutions also require a bit of further explanations on how to work with them. And this benefit of a very efficient and quick inference is, I think, due to the layers being implemented in CUDA. So they implemented them in CUDA, and it's important that you know that their original CUDA implementation is open source. It was originally intended to be used with MXNet, but already several repositories around the internet adapted them to use with other frameworks such as TensorFlow, and if you work with Keras, then this will also work for you, etc. Yeah.
How can it be that they add so? Because the gave us, it seems that for each
Convolution.
convolution, you add a lot more parameters. You add 18.
Okay, so how can it be that it adds so few parameters? So for example, because they only do it on 3 convolutions. So yeah, that's part of the reason, I guess. Yeah. So, but it's like we can sit on it later, and you can see easily that that's the number of parameters that it adds. Yeah, let me finish just like 2 slides, and then we can have more questions. So. As we expected, the receptive field is affected by the object size. Just like we saw in the intuitive cherry-picked examples in the beginning, they analyzed all of the objects in their data set, or many objects in their data set, and they checked what is the receptive field of the deformable convolutions for the small objects, the medium objects, the large objects, and when the convolution is on top of the background. And they saw that for the large objects and for the background, the offsets were largest and the receptive fields were largest, just as we would expect intuitively from this mechanism. But what if maybe the deformable part and sampling the image in an irregular grid, maybe it's not really important. Maybe the only thing that's important here is just the dilation, is just sampling further context. So using dilated convolutions in the last layers of the feature extractors that are used for detection is already standard practice in detection networks. And it does improve the performance, but usually it's used with. I'm sorry, I'll explain what are dilated convolutions for a second. So this is a standard convolution, and a dilated convolution is just keeping it a square but putting holes between the sampling points. So this is with a dilation of the hole size is 1, and here the hole size is 2. Or it's also called the dilation rate, and usually people use the dilation size of 2, and they show that for the COCO applications and some segmentation applications, it's even more optimal to use a dilation size of 4 and 6. But it depends, the optimal dilation depends on your architecture, it depends on your specific image, and it even depends on your specific object. Because as we saw, for large objects and small objects, the dilation is different. So even if the only important thing here is the dilation, still a solution like that will be desirable because the dilation is learned and adapted to the local parts of the image and to the object that you are looking on.
Basically, it's a generalization of that dilation.
It's a generalization of convolutions in general and dilation convolutions specifically. Yeah.
You might say that it's a dilation convolution on acid.
What? Sorry?
Dilated convolution on acid.
On acid, yeah. Dilated convolution on acid. That will be the title of my next talk. I love it. So, but they showed that if you use their method, then it improves even on the most optimal configuration that they could use when with just dilated convolution. So it even improved the results further, and it didn't require any manual tuning or hyperparameter sweep of the dilation hyperparameter. Okay? So these were deformable convolutions. Now we have 2 choices. One choice is to move on to the next paper, which can be feature pyramid networks or focal loss. And the second choice can be to like answer questions. So Dotan, either you decide or we can have a vote. Okay? Yeah. So anyone that has more questions can, of course, come to me later and ask them or send me an email or whatever you want. So feature pyramid networks. This is this is a paper by Facebook AI Research Group, one of the best object detection and deep learning teams in the world. And as I told you, the previous paper tried to answer the challenge of the anatomy and the pathologies the medical pathologies that we are trying to look for. The previous paper tried to answer the problem that they don't have they have an irregular shape and a deformable shape. And this paper tries to answer the problem of the object being small. So this is a spine fracture, a fracture in the spine. You can see it here. And what is the problem of what is the problem with a small object? Why are they difficult for neural network? So just as an intuition, if we perform max pooling on and each of the and we have several neurons next to each other, and this neuron's receptive field covers mainly this area, and the receptive field of this neuron covers the fracture, and the receptive field of this neuron covers this area of the bone, then even if we have really good features, and we know that here this neuron indicates that there is a bone under it, and here it indicates there is a fracture under it, and here it indicates there is a bone under it, after we perform max pooling on the three of these neurons, we lose the spatial order between them. We know there are bones there, and we know there is something like a hole there, but a hole is not necessarily a fracture, and we need to understand the spatial structure between the things in order to really classify fractures. So this is one intuition for why convolutional neural networks have problems with small objects. This is not the only reason, by the way. Another reason is class imbalance. Small objects are more underrepresented in our data, and this is also another reason. But this paper deals with the problem of not having good enough features that describe the spatial locations. So the motivation for this paper is a lot of papers before did things similar to that. Maybe instead of just predicting using the deepest feature map, maybe we can combine somehow feature maps from several depths. And a lot of papers did it before, and they also like DenseNet as well. DenseNet also did something like that, but DenseNet it's part of the architecture. It's like you can say that ResNet also does it, because ResNet also has skip connections. But I mean that you take your final feature map that you predict from. We'll see it in a minute, okay? So we can assume that features from shallower feature maps can be important to classify small objects because they were developed before doing too much max pooling, so they lost less spatial information. So it would be desirable to use them when we classify small objects, but we miss them because the network, we use only the last layer, and we could say that we can hope that the network will be smart enough to develop good enough features before it does max pooling, to identify that this is a fracture before it does max pooling, while it has the lower level features. And we can hope that it will work, but as we know with neural networks, a lot of times, if you don't force the network and you don't encode your prior knowledge of the problem into the architecture's design, then the neural networks don't behave optimally. And although they could fit many types of functions, they tend to fit not the optimal functions unless you encode your prior information into the design. So there are a lot of ways to combine the shallower layers and the shallower feature map, but this is currently the most popular implementation. And the reason that I feel confident to say it is that in the last COCO object detection competition in the end of 2017, all four top competitors, all four top submissions, used feature pyramid networks as a major component of their submission. And it improves object detection accuracy by about 10%. So what I really love about this paper is that it puts simplicity and elegance as a major part of their work. So the first element of it is they said, we already know that in convolutional neural networks, if we use image pyramids, some of you maybe know it is test time multiscale. So I'll explain what it is in a minute. If we use an image pyramid, it really improves our way to deal with smaller objects. So what is an image pyramid? We take the original image and we scale it up to many sizes, or scale it up and down to many sizes, and then small objects appear larger and are less affected by the pooling operation, and it has several other advantages. And then we pass, if we use ResNet 101, for example, we pass each of these scaled images separately, and we have nominally like 10 sizes, for example, patch each of these 10 images separately through the 101 layers, and get separate predictions for each of them. And this works quite well. The problem with it is it's not really feasible for most applications because it requires a lot of time to make so many forward passes of large networks. So they try to imitate or take their intuition from image pyramid, which has already proven itself. And in many of their design choices in the paper, they try to just, instead of inventing something from scratch, they try to imitate something that already exists and is known to work. And you can see that even in the diagram, it looks quite similar to image pyramid. And we'll talk more about it in a few minutes. So you can use feature pyramid networks as a part of the RPN, the region proposal network, the first stage of the faster RCNN, and as the part of the second stage of the detection network. So it is combined differently into these two parts of the network, and we'll talk about each of them separately. So for combining it into the RPN, and now you will understand what feature pyramid networks actually do. We take the image and put it through our feature extractor. This is our feature extractor, for example, ResNet 101. And then we have something that they call a lateral connection, which is a one-by-one convolution. A one-by-one convolution that keeps this feature map the same size, but transforms it to have 256 features. And then we take this new feature map and we upsample it using nearest neighbor upsampling with a scale factor of 2 in each dimension. So we enlarge it, and since our pooling in the original feature extractor was also with a factor of 2, then now the scaled up feature map is the same size of the feature maps of the previous stage in the feature extractor. So now we can choose a single feature map from the previous pooling stage in the feature extractor, and we can combine them using a one-by-one convolution on this feature map and summation of the two feature maps. Not concatenation, summation. And we repeat this process several times. Actually, this process is repeated something like 5 or 6 times, depending on the implementation. And then we get a pyramid of feature maps. And the shallowest feature map contains features from contains features that were transformed from all or almost all of the levels of pooling in the original feature extractor. And then, for each of these feature maps, we predict separately. We predict bounding boxes from this feature map separately, and this one separately. And there are only 3 feature maps drawn here, but in practice, they use 5 or 6, depending on the implementation. So which layers do we choose for this? Which layers do we choose for the lateral connection? Does anyone have a guess? Yeah, so we don't take only shallow layers. We take both shallow layers and deep layers, but we take one layer from each. There are 5 pooling operations in the network. So before each of these pooling operations, we take the output of the last convolutional layer before this pooling operation. Why? Because, as we said before, the pooling operation is the component that causes us the trouble with the small objects. So after we perform the pooling operation, we will lose information. So we want from each pooling level to take some information, some features, and we choose the last layer before the pooling because intuitively it has the most developed features for this level of spatial information. Okay? Yeah.
Is it quite similar to unit architecture, but you predict for each?
It's similar, but you predict from each level. Yeah, as I said, it's very similar to many other architectures. They didn't invent the concept of using features from shallower levels. It was mentioned in dozens of papers, but this group and also several, maybe a few other groups in the same time are the first to propose this mechanism of predicting from several stages. By the way, SSD, the SSD detector, also predicts from several stages, but it doesn't use the shallower features. It starts from the top and creates new layers, but it never combines the shallower features, and that's where SSD misses. Okay? Yeah. Sorry, yeah, you raised your hand before. Yeah.
They've been trying to only predict all the features, all the input sizes from the highest resolution.
This one.
Yeah, exactly.
Yes, and I will show the results in a few minutes. Yeah?
I'm not sure I understood. So from each level for not showing, you take the feature map, you move it to the one by one, and then you sum all of them.
From each level, for each, I'll explain so that everyone can hear. I won't repeat the question. I'll just explain the process. Okay? Thank you. So for each pooling operation, you take the output of the convolutional layer before it, and you put it through a one-by-one convolution to reduce its number of features to 256, and then you sum it with the upsampling from the top-down connections that they have here. Okay? Is that?
It's all summed up, all the 5 outputs are summed together?
This feature map is a result of a summation of all of the 5 outputs, but the one above it doesn't include the one below it. It's only a result of the summation of the ones above it. Okay? And yeah. Okay. Yes.
Wouldn't the normal feature be more convolution
More lateral connections?
convolution and layer from the lower level lateral.
Mm-hmm.
So the very small object will have also
I think I would love if we could answer this question later, because I think it's less of an understanding question and more of an intuition question. So if anyone has more understanding question about the concept, then it's important to ask them now. Yes?
I assume the training is end-to-end.
The training is end-to-end, yes.
So you have a lot of ends here, several predictions.
Yeah.
So,
We will get to it in one of the next few slides. How you train it, we'll get to it actually, I think, right now. So now that you have all of these 5 pyramid levels, and we see 3 of them here, we use a predict head on top of each of them, which predicts the bounding boxes or the proposal bounding boxes. And how do these heads work? They work just like the head in faster RCNN. This is, by the way, part of what I said of the simplicity of their design. They tried not to change too much. Keep all the mechanisms the same, just add as few as possible. So this is taken from the faster RCNN paper. This is the original paper. This is how in faster RCNN, you didn't have this feature map. You just had the deepest feature map. And you put a 3x3 convolution on top of it. And for each location of the 3x3 convolution, you turned it into a vector of 256 dimensions. On these vectors, you use the 1x1 convolution, one 1x1 convolution to predict the coordinates of the bounding boxes for that spatial location, and one 1x1 convolution to predict the probabilities of being an object and the probability of not being an object. So here you use the exact same predict head on each of these layers separately. And not only do you use the exact same predict head, it's not only that you use the same architecture for all of them, you also use the same weights for all of them. They share weights. So if the predict head on this layer predicts a false positive box, and then it's punished in the backpropagation mechanism, and the weights in the predict head change, they change for all of the layers together, okay? And they tested it experimentally, empirically, and they saw that using different predict heads, if they don't share weights, then it doesn't really improve the performance. More about how they train. So for each of the levels of the network, so we have 3 here and 2 more here, they assign a different size of bounding boxes. So the deepest bounding box is only trained on the smallest object. And the top bounding box is only trained on the largest objects. This is similar to the concept of anchors in faster RCNN, for those of you who are familiar with it. Only here, the anchors are trained on separate layers. The anchor of each scale is trained on a separate, completely separate layer. And the reason for that is that we would expect that this layer will contain the most relevant information for small objects. So we want it to specialize on small objects because it's a really difficult task. So we want it to be the best it can on small objects. And that's the intuition behind it. Okay? Great. So this was about how to combine it with RPN. And now we will talk about how to combine it with the second stage of the network, fast RCNN. So a short reminder about how fast RCNN works. So with the feature map, and with RPN, we get the proposals on the image. We get about, for example, 2,000 proposals. And then we use ROI pooling or deformable ROI pooling to pull each one of these proposals from this feature map. Okay? But now that we have, so in faster RCNN, we didn't have these layers. We only had this layer, and that's where we pulled the bounding boxes from. Now that we have many layers of different spatial resolutions, maybe we can also pull the bounding boxes from these layers and not only from the deepest layer. And that's the concept. But how do you decide which layer do you pull the ROI from? So here again, they use the concept of simplicity. And they said if you're trying to imitate image pyramids, we can just use the decision rule that is already known to work with image pyramids. So there is a very clear formula that is used. And this is the formula, the floor of 4 plus, you can read it, okay? So you can read it, and now I'll give examples of how it works. So let's say that our W and H are the sizes of our proposal, the width and the height of the proposal in pixels. So let's say that the proposal is of size 224 by 224. What we get here is 4 plus log 2 of 1, which is 0. And the end result is 4. This means we ROI pull the result from the 4th layer. And we'll talk about the intuition behind this in a minute. And when we take a proposal which size is 112 by 112, then the result will be 4 plus what you can see here. And the result of this log operation is -1, of course. So it will be 3. And for a larger bounding box, it will be 5. Okay, so you can see that this formula enables us very efficiently to ROI pull larger bounding boxes from shallowest layers with less spatial resolution information, and smaller objects from the layers that contain the most the information with the most spatial resolution. By the way, 3 is the number for this layer, 4 is the number for this layer, 5 is this layer index, and so on. Or actually, this is 2, 3, 4, and so on. 100 by 100. Yes, it's still a relatively big object, and we have one feature map below it to take care of objects that are smaller than that. We have just one feature map below it. She said 100 and 100 is still big, but we use a relatively shallow layer to pull it from. And maybe we are wasting the high resolution information there on relatively large objects. I'm sure that this can be optimized more, but it works quite well. Okay? So in this formula, we saw there is like a magic number here, 200. Yes. Sorry?
The flow can go inside the log and canceling 200. Why there is a 4 in the formula?
The 4? Okay, maybe it doesn't really matter even if it is. That's the way they decided to build the formula. Okay, so it's for ease of it's to make the formula more friendly actually. And we saw that there is a number here, 224. It looks like a magic number because it's also the size of images in ImageNet. So that's the reason we use this number here layer number 4 is actually the layer that the ROI pooling is performed on the original faster RCNN with ResNet 101. It's pulled from layer 4. And since ResNet was pre-trained on ImageNet, and all of the images in ImageNet are pretty much objects of this scale, then if we get an object of this scale, we would like to pull it from like the default layer to pull object that has proven itself so far. So that's the intuition for the 224 number, and that's also why they have 4 here, because then when you have an object of size 224 by 224, the log goes to 0, and you remain with the default layer index. Yes?
Explain about the scores.
Explain about?
The dimension of the score.
The what?
Dimension of the score.
The dimension of the score? The units of the score, you mean? Sorry, I'm previous? Okay, yes.
Yes, here.
Yeah.
2K.
Okay, so K is the number of bounding boxes that is predicted for each spatial location. It's also called the number of anchors, if you know it. So for each spatial location, I don't only predict a single bounding box. I predict something like 9 bounding boxes or 15 bounding boxes. So for each of these bounding boxes, for each of these 9 bounding boxes, I want 4 coordinates and 2 probabilities. So this is the 2K and the 4K. It's not 2,000 or 4,000. It's just like 2 times the number of bounding boxes that I'm predicting in that spatial location. Okay? Okay. Let's move on, and we are close to finishing this. So regarding RPN experiment results, they try to test it. It's relevant to some of the questions that you asked before. So they tried not to use the top-down connections, only use the lateral connections, and not, which means predict from each level of features, but don't combine features from deep layers and shallower layers. And they saw that it didn't even improve on top of faster RCNN. And they tried to use only the top-down connections without the lateral connection, and it also didn't improve. The only other thing that they tried that did improve was creating all of this pyramid, but not using all of these predict heads, using only a single predict head from the bottom. And since the bottom contains a combination of all of the features, intuitively maybe it's enough just to predict from it and it's more efficient. But in practice, they saw that it's not enough, and that it's not enough, and that it does improve, but it lags far behind the full feature pyramid network solution. Regarding fast RCNN, they asked themselves, maybe if we use feature pyramid networks on the RPN, maybe it's enough. Maybe it's too much to put it on the fast RCNN as well. Maybe it's not improving anything else. So they trained the RPN separately using feature pyramid networks, recorded for each image the best proposals that they got for that image, and then trained fast RCNN separately using these proposals. From the beginning of the training, fast RCNN only got the best proposals. It was not trained end-to-end. And still, fast RCNN improved the results by another 5 to 10%. So this component of fast RCNN is important. And we talked about this decision rule here, and it's nice, but they saw that even if we don't use it, in fast RCNN in the second stage, we only pull from this layer, from the deepest layer, we don't get a large difference in results. So fast RCNN is less sensitive to which layer you pull from. You just need to pull from the last layer with the most information. And some other neat things that they saw. Of course, it improves especially for small objects, the results for small objects. And the test time per image on a single GPU is less than a single-scale non-feature pyramid network of the same architecture. So the feature pyramid network, although it is a more complex architecture, it's faster, and it's out of the scope to explain exactly why, but Ross Gierschik, which is one of the writers of this paper and is very well known, wrote like a comment on GitHub explaining that. So this is feature pyramid networks. And before we need to summarize, if someone has a really, really important question, otherwise you can come ask me, I'll stay here. OK? Great. So we won't have time to cover focal loss, but I will publish my slides online, and hopefully maybe they will be enough self-contained for you to look at them, and maybe we will see each other some other time. So to summarize, object detection, I really believe that it's a revolutionary technology that is progressing really fast and has the potential to change every industry. And the latest major advances, the latest major advances in object detection, except for being really creative and mind-blowing and fascinating to learn about, also address some of the most major problems in many data domains, but also specifically in medical imaging. And the solutions that we talked about earlier, except for focal loss that we didn't have time to cover, were small objects, which feature pyramid networks give a very elegant and efficient solution for. Deformable shapes, which the deformable convolutions and deformable RI pooling give a very elegant solution to. And extreme class imbalance, which focal loss gives a very nice and innovative solution for. So as usual in deep learning, like what we said in the beginning, it's not rocket science, and I think that many engineers can understand the concepts and implementations, but the question is, what can we do better in order to make this information more friendly and reduce the time that is required to understand it by a factor of 10. Thank you very much.